let's go ahead and start. This is week 5, episode 9. And we're not going to have week 5, episode 10 tomorrow because it's a holiday. So I guess it's good for you guys. Have a longer vacation. Maybe it's time to go out finally and see the nature a little bit. Good. So the topics today are DNS. Originally, I thought I'd talk about email next, but I find that DNS is probably a better topic to start first, and then next week we'll come back to email. So today, the breaking of the topic is this. So DNS is going to be cut in 2 parts. The first part is more talk about the system, how the messages get route around in the structure of this DNS system. Second part is more about the data. So all these entries that are maintained on the DNS systems are essentially these name IP address mapping, which you will hear about a bit later. But it's a huge database in a sense, DNS. So we'll hear more the data side of it in the second part of the lecture today. And then we'll have the quiz number 9, okay? This is going to be a more challenging quiz. It's going to be slightly open. Unlike the previous 2 that are very specific, targeting HTTP messages. And then the rest of the lecture today is just going to be the video walkthrough of PA5. Don't worry, PA5 is very simple. So the walkthrough is very brief, only like 7 minutes. So that is today, and that's begin. Next is chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. Well, that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So hey, how does the web browser know? What is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers, and there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy, and some of them sitting lower. What's a bit special about DNS here is, if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol. in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it at the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly. Right. DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the host name to IP address translation. It does 3 other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with the host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as .google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com, okay, all the emails destined to this domain should send to this machine, smtp gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP addresses each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slide, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server. But it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growing large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances is higher that you need to do the testing longer, debugging longer. Not good either. Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, poly.edu, ums.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these servers at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's contacted by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping. Get the mapping and then return mapping to the local name server. Now, the trick part is this. Okay, when I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers. But each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites. 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially very few of these rule name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top level domain servers. They're responsible each for a different top level domains. So top level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server, and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries really. Right? Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when the host makes a DNS query, query is always sent to the local DNS server. Now, these DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course, forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. All right, so nice. But be careful. These entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client. It's not exactly server, it's something in the middle, helping relaying the queries, relaying the answers. Okay, so helping forward queries into the hierarchy if there's no hit here at the cache. So far, we've learned that there's a hierarchy in the DNS servers. There's the top, second, and the third level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS, poly here needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy. And the server will reply with something like this: name of the server to contact. Okay, someone who might know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes. Client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. DLD DNS does not know the IP just yet, but top-level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traversed back. And root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on name servers that's high up in the hierarchy. There's going to be a lot of query comes to the root. And there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same. Right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server. All right. So that was part 1 of DNS. Let's see if you have any questions. Okay, so there's just one administrative questions. Yes, PA4 is due this Friday. So even though it's a long break, don't forget about PA4, submitting it. So are the Q7 and Quiz 7 and Quiz 8. So if you have not yet submitted during the lectures and not yet posting on the Facebook pictures, please do so. And now let's go into the second part of DNS. DNS servers also cache data. And this is not the first time we hear this term, caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects so we could reduce delay, we could save some network bandwidth. You see here, DNS for the same purpose also caches IP, name, mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay? Again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out. But the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay, well, to be more precise, the resource records. Okay, and each look like this: a tuple of 4 elements. This is usually the host name, and this is the IP address, and this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname at the name and IP address at the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here. The C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup2.ibm.com, right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry, right? So the name there is a domain, okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next thing, the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS servers saying, no, that's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now in order for the receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the in the answer entries, however, then you see the full RR, the full resource records. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used. Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so two things you need to do. First, register your domain name with the DNS registrar. Now being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the network solution there, will try to insert two records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now back home, you need to set up a couple of these authoritative server for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website. Attacking DNS, this is the last bit of DNS. So we're going to talk about attacks in three parts. First is attacks targeting the hierarchy of the DNS. Second is to target more the client who need DNS service. Third, then is to exploit the DNS service to try to pull off attack for some other targets. So let's go back to attacking the hierarchy. So a hacker could actually hack down a number of machines around the internet and have these machines bombard the root servers with lots of DNS queries. Right, so having very few root servers around, this can potentially be dangerous and bring down the DNS service entirely. But nowadays, it's hard to pull off, mostly because the local DNS servers will cache the TLD servers. This allows all the local servers to bypass the root server entirely. Right? So there's not much traffic going to the root. If the zombie machine sends a lot of queries, chances high that they'll only go to TLD instead of the root. Right? Not to mention that one could set up firewalls. okay, nearby the root servers. So those very few root servers are well protected in a way. Now, attacking the TLD servers then is more feasible, all right? Because queries then all go to the TLD these days. Good, so it's more dangerous. But the thing with the TLD server is that the number of these is way higher than the number of root servers. So the hierarchy there is pretty robust, to be frank. The second type is the redirect attacks, but I would rather call that this is attacking the user of the DNS service. First is the man-in-the-middle attack. What the hacker does here is just to intercept the queries. Therefore, it's not going to reach anyone in the hierarchy, and therefore no answers back to the users. Second one, on the other hand, I think is meaner. DNS poisoning. So the hacker there is actually sending false replies. So when local DNS server caches these replies, the users will be thinking, "Ooh, I thought I'm going to the www.google.com, but it's actually going to a hacker's website." Not very good. So nowadays, network admin for the local DNS servers needs to be careful and check the sources of these replies. Last one, exploiting DNS for DDoS. We actually hear about this already. So this is in chapter 1, I believe. Okay. So people are sending queries. Hackers can spoof these queries and replace the source address, okay, with the IP address of the attack target. As a result, the servers in the hierarchy will be all sending replies to this guy here, okay, and therefore denying this machine here to go out and reach the rest of the internet. But this is also a bit hard to do because you have to hijack enough of these queries. You need to spoof enough of these queries, right? So you need amplification in order to make sure that the service is really denied, okay, at the target IP. All right, so that's all about DNS. I hope it's clear. There's just one minor clarification before we talk about quiz number 9, which is this. By authoritative replies, I actually said that it's coming from the authoritative servers, but no, there are actually the entries kept in TLD server. Therefore, they should be coming back from TLD servers instead of authoritative servers. All right. So there are essentially these NS entries. Good. So yeah, quiz number 9. I don't know about you. Right? When I was in college, well, many years ago, every now and then I thought, hey, it's really time to get real. I don't know what's the point of attending all these lectures and professors keep mumbling about all these things that are very abstract, that I might not really have an opportunity to exercise on. So it's time to get real. Okay, pretend that you're asking the same question. You decide that this is enough college education for you. Holly's not encouraging it, but just, a scenario. Pet book is totally better, you said. A social network for pet animal lovers, using the pet's picture, impersonating your pet, is going to go wild. Okay, it's going to do better than Facebook, better than Snapchat, better than IG. All right. So this is the banner that Polly has retardedly designed and copied from Facebook. Okay, by the way, this is Honey, Polly's pad. Okay, now here's the question. Being your own CTO of your own startup, the pet book, okay, how would you first structure your pet book server network? Okay, because essentially, if you think about Facebook or IG, it's a gigantic database, okay, of all these data uploaded by the users. All right, so your pet page essentially contains photos, chats or notes, status report, maybe short videos, etc. Okay, it's essentially a huge database, right? So how are you going to structure your database? Okay, is it going to be distributed, or centralized? Think about DNS. It started off centralized and turned out being very distributed now. Okay, so how are you going to structure your pet book server farm? All right. And question number 2. Okay, how are you going to direct the pet page query so that the server load is somewhat balanced and so that we minimize the delay? All right, so your friends is gonna, come check on you every now and then, check on your pet page every now and then, right? So if the friend is asking for your page, how is that query gonna be forwarded in this network structure, this server structure that you established? All right. So you see here, quiz 9 is more open. Of course, you can borrow the experience you hear from DNS. Probably you can also borrow experience from web. And you can probably also Google a little bit. So let's make it about 3 minutes, okay, for this quiz. So you have 3 minutes to think about, okay? And those who have some ideas, feel free to type up. This one might be a bit challenging at the end of 3 minutes. It might still be hard to say. So don't worry. You can always go back to the Facebook, the picture, and talk about it. All right, so start counting, 3 minutes. Hey Siri, set a timer for 3 minutes.
Okay, 3 minutes and counting.
All right, so keep thinking about it, and we move on to the third topic. And if in the meantime, when you're attending to the video walkthrough of PA5, you came up with something, just type up. And the video for PA5 is going to be very straightforward.
This is PA5 video walkthrough. Now, the goal here is to extend your PA4.go such that we have the PA5 that works more like a file upload server. If you recall in PA4.go, what you did there is to allow one file upload, and then your program terminates immediately after that. And if you think about it, that was actually not quite a server, isn't it? A server is supposed to be always on and waiting for the client's request. And it is supposed to run forever. And you're right, PA4.go, they're allowing only one upload. Is not very professional, all right? Some people might be embarrassed calling PA4.go a real file server. So in PA5.go, you're asked to extend PA4.go such that it will look more like a real professional file upload server. Okay. Now, to be exact, what you'll be doing is, well, pretty much following the algorithm, the steps that we've described in PA4's description, but change it a little bit, right? To be more specific, let me go through what your PA5.go should be implementing. Step 1, listen at the port that you're assigned and wait for an upload request. Read from the socket first for the file size. And then you may begin to read one line at a time. Prepend the line count, and then store the new line into the new file, whatever .txt. And step 3 and 4 will continue until the entire file is exhausted. And then you send back a message to the client telling what's the original file size and what is the extended file size. Step number 7, close the data connection. And here's what the difference is. Go back to step 1. So in PA4.go, the algorithm, step 7 is just simply close the connection and terminate the program. But in PA5, don't terminate the program and go back to step 1, where you listen again at the port that you're sitting in and waiting for a upload request. In case there's another dial-up, read from the socket first the file size and go on and on and on. And if you think about it, this assignment is very light, very simple. Some of you might be thinking already that, hey, isn't this simple? Why don't we just make this the whole thing in a for loop and never coming out of the for loop, then we get this forever looping file upload server. You know what? You're perfectly right. What you need to do is just to go off and implement that idea. So the rest of the walkthrough is more just that Poly will be using server 102 as an example. How you extend server 102 such that it will be a forever looping server that accepts a short message from a client. All right. Now, in this example, what you'll be doing is to create a server loop.go. Okay, so you'll be creating server 101, the looping version in a sense. Okay, so you'll be typing up this code. You see here, the usual suspect, package main, and import 3 of the packages that we use a lot, the check function, and then the main program. All right, so launching server and listening for TCP connection, defer closing of the listening socket, and the rest of it is essentially an infinite for loop. Okay, and inside the for loop, the lines we see in server 102. Right? So accepting a connection, deferring closing of the data connection, the file connection, read a string, print the string, write a message back, and says in the message number of bytes received, right? And flush the message out. That's all. Now let's give it a go. Don't forget to replace this part of the code block with the port number assigned to you. Now let's execute server loop.go. You see that the server is launched and it's waiting for the client to send the request. So let's execute client 102.go. What's more interesting here is, hey, once you've done client 102.go, the server prints one line, hello world. And wait again. So that is supposedly the behavior of the server. So finishing one service and wait for the next one coming. So that's runs client 102 once again. You see then, another line of hello world being printed at the server side and server back to wait another client request. So that is server loop.go that runs hopefully until forever. Okay, demo time. So let's do server loop.go. All right, server is launched and waiting for request. So we do the client 102 in the terminal at the lower left corner. There we go. Client quickly finished execution, and server actually also pretty quick, printing "Hey you," but it's now what? Waiting for the second request. So let's execute 102, the client again. There you go, another "Hey you," and we could do this again and again. The server will continue to wait and serve, and wait and serve. All right, so that is what Poly is expecting. Your PA 4.go needs to be extended such that it will be serve and wait the next request, serve, wait another request, and serve. And that should go on forever.
All right, so that's all for today. And we do have a team here. So team 1 here is actually typing quite a bit up. Yeah, so live chat does not allow more than 200 character input. So yeah, Rocket, have you experienced setting up your own service? Sounded like you did. So you will try to use the cloud service that's existing until the number of followers is significant enough to set up your own server farm. All right. Let's see. Okay, you'll choose Nginx. Okay, so you'll be building your database on top of Nginx HTTP service. All right. I see. So this is more about the strategy of setting up the hardware infrastructure. I see. Good. Yeah, and you know what? The time is up. Also, just to add a little bit more to David's question, even though that I ask how you structure it, how you direct the queries, such that the load can be balanced, therefore the delay can be lower. But feel free to think for other metrics. For example, what David said there is more towards minimizing the overall network traffic due to your service for the internet as a whole, which is also a good thing because generally when the traffic being generated by your service is lower, the delay will also be lower. The reason that I mentioned you want to balance the load is usually because certain servers, if you're not careful, might become the service bottleneck. If you think back, DNS as an example, the root server there in the original recursive query model becomes the bottleneck of the whole service, even though the structure is large, even though you've invested a lot of money. It might not really be efficient. Okay, so in addition to the money that you've put into your server farm, you do also want to get some very good engineers who actually study hard for introduction to computer networks so that they can design the network structure and then design the model of the messages exchange. Therefore, the system is going to be balanced and going easy and not having serious bottlenecks. All right. And that's all for this week. Enjoy the rest of the long weekend. I'm just going to end the stream now.